Yeah, we are on now. Yeah, so yeah, let's get started. Welcome everyone. This is Happy New Year, first of all, and welcome to our first webinar of the year. Um, Before we start, and I introduce the speaker, let's just go through some basic housekeeping stuff related to the crowdcast system. So on your right hand side, you have the chat. On your right hand side of your screen, you have the chat. Above it, you have some icons. There is one icon with the question mark. That's the Q&A. So it would probably be, given the time, the constraints we have on time, it's probably better, if possible, hold on your questions until the end, unless you have something pressing, during the presentation that you want clarity. Otherwise, just use the Q&A and post your questions there. If you are finding it hard to to find this icon, this is the same with me. Sometimes this crowdcast system, just type your question on the chat. That's also okay. So that's it. So let's get started. So it's a pleasure to introduce our friend Mahdi Chameni, who will be presenting about physics-informed quantum communication networks, a vision towards the quantum internet. So Mahdi is currently a PhD researcher at the Electrical and the Computer Engineering Department at Virginia Tech. His research interests includes quantum communication, quantum networking, and quantum machine learning, with applications to wireless networks. So Mahdi, great to have you with us. The floor is
Thank you.
yours. I look forward to your talk, and I'm sure everyone is excited to get some insights.
Thank you, Baboli. Thank you so much. And I'm really appreciate this invitation to be here with everyone. And if anyone has any question, feel free to interrupt me during the presentation. It's totally okay. We can answer any question during the talk. So, as you just said, I did my bachelor's in electrical engineering, with the focus was on communication systems and RF engineering. Then in my master's studies, I focused a little bit on physical layer security in wireless networking. Then currently in the PhD, working with Professor Walid Saad, I'm working on quantum communication networks and quantum machine learning. I recently finished a visit to the University of Massachusetts Amherst, where I worked with Professor Don Towsley and collaborated with multiple people from the Center of Quantum Networking, funded by the NSF. And I worked on quantum networking and quantum error correction. I have also some entrepreneurial activities during my master's, and that is just an overview. So today we're going to be talking about quantum communication networks in general. We'll talk a little bit about the fundamentals, the background about the topic, the advantages of quantum communication networks, what are the current challenges and problems facing them, and how we can actually optimize certain parameters in quantum networks to enhance the performance. Then I will focus a little bit on one of my papers that is, so the first part is based on our recently accepted IEEE Network Magazine article, and then I will be explaining the details of another paper that we published on entanglement rate optimization. And finally, I will be talking about some future research directions and outlining our works on that. So in the beginning, we know that we are living in a world now with continuously increasing number of connected devices, where there is enormous amounts of data that is being generated every day, where everything around us is being connected, from our houses, our personal items, our work environment, study environment, everything is being connected. And to deal with these new technologies, the next generation, so recently 5G started being implemented, and researchers are now focused on the work on 6G wireless communication systems, which will have actually highly increased complexity to be able to provide services like virtual reality, metaverse, digital twins, and advanced brain-computer interfaces, holographic telepresence, among many other applications. So to do so, we need actually to achieve a significant increase in the throughput or communication rate in the network, and that requires in advancing the hardware or the computing chips that we have in today's architectures, communication architectures. So over the years, Moore's law, which says that the number of transistors installed on a microchip would double every 2 years, was actually the base on which the developments in semiconductor technology were happening over the past 50 years. But recently, this law started being violated, and electronics became so small to a level where the quantum effects can no longer be ignored when dealing with designing such small chips. So we need to consider the quantum effects. We need to think about developing some quantum technologies. And this motivated developing quantum computers, which started long time ago. And quantum computers, they can provide us with superior computational speedups. This is a picture of a quantum computer, which is actually most of it is kind of gold and other metals that is used to cool down the actual computer, which is inside. And such quantum computers are able to handle exponentially large data in terms of dimensionality, which is pretty important in the future of smart cities and smart homes. And this, the developments in quantum computers over the years led to great developments in machine learning, artificial intelligence, and communication networks. And this field actually also witnessed the development of various superior quantum algorithms, like Shor's factoring algorithm, which provides an exponential speed up compared to classical factoring algorithms, and Grover's search algorithm, which provides polynomial speed up. Actually, Peter Shor, he got Nobel Prize last year for his developments and his contributions in the field of quantum computing. And this factoring algorithm is one of the biggest achievements in history of quantum computing. The reason for that is that Shor's algorithm, when implemented on a fault-tolerant quantum computer, it can break today's RSA encryption. And today's RSA encryption is actually the encryption protocols that are used to encrypt almost everything that we deal with. So our banking systems, our communication networks, all our devices that we use, they rely on RSA encryption, which assumes that factoring large, like doing prime number factorization of very large numbers, is a process that takes classical computers, even supercomputers, it takes them like many years to be implemented. But if we are actually able to build a quantum computer that is fault tolerant and that can perform error correction, and we are able to run Shor's algorithm, we will be able to break the RSA encryption. And this is a very strong risk that we are facing for the future of our all our technologies that we have. And here comes quantum. So a technique called quantum key distribution, which relies on quantum mechanics, actually is able to provide unbreakable secure communications compared to the classical techniques. So by relying on quantum cryptography, we are able to develop like post-quantum cryptography protocols that are secure against quantum computer attacks. So this motivated the developments of networking and communication protocols for quantum computers, so that we are able to communicate securely even if quantum computers exist, which will threaten the encryption protocols that we currently have. So in order to apply those secure communication techniques, we need actually a network of quantum devices. So a quantum communication networks is a network of connected quantum devices that are able to share quantum states and quantum data and communicate securely between themselves. So this is one of the main motivations for why one needs to consider quantum communication networks. So quantum communication networks rely on the principles of quantum communications, which are inherently different from the classical communications that we have. In quantum communications, we share qubits instead of the regular 0-1 classical bits. And a qubit can actually be in any superposition of 0 and 1 at the same time, where a state psi is resembled by C0, some amplitude C0 with the zero state or the 0 bit, plus C1 times C1, the 1 bit. So it is kind of a superposition of both. And a main resource in quantum communications is called the quantum entanglement, which is a really important part in to be able to do quantum communications, to send quantum data. So quantum entanglement, or according to Einstein, it is the spooky action at a distance. It says that when we have two qubits that are entangled together, they become correlated to each other in a way that no matter how far away they get separated from each other, measuring one of them will directly affect the state of the other qubit. And the most general and basic entangled pairs of qubits are known as Bell states, which take this form where it says either 0, 0, for example, or 1, 1, or 0, 1, and 1, 0. So here you cannot, those states are perfectly inseparable from each other, and those are entangled states. Moreover, when we do a measurement of a quantum state, so we put our data or information inside a quantum state or a qubit, and we send it over quantum communication, which we will explain how it is done. So now we need to read out our data, so we need to perform quantum measurement. However, quantum measurement is a probabilistic operation, and actually, whenever quantum measurement is performed, you will get either 0 or 1. So if we say a qubit is a superposition of 0 and 1, when you do measurement, you will either measure 0 or 1. So if we go back to our state psi, if we do the measurements here, we will get, with probability magnitude C0 square, we will get the state 0 or 1 with the other probability. And you can imagine this as a coin spinning inside the box. So if you have a coin, or let's say you get a coin and you spin it, in this time it is spinning, it is not 0 nor 1, because it is kind of in between. Until you measure it, you stop it, and you will either see heads or tails, or 0 or 1. So that's how quantum measurement either gives you a 0 or a 1. And quantum communication relies on not just measurement, because measuring a qubit alone will make us lose the information. We need to do the measurement with other quantum gates and operations, and we will perform protocols called quantum teleportation to be able to send a quantum or a qubit or a quantum state from one side to another. And I will not go into the details of those protocols. So we will focus more on quantum communication networks themselves. So quantum communication networks, they include many components that are required so that we are able to develop or build a network. We start with single photon sources. So we need single photon sources that are able to emit single photons, and those single photons will carry the quantum state. So as we said, a quantum state is a superposition of 0 and 1, like between two independent states, between heads and tails, for example. So if you consider a single photon, the photon has polarization. So it is either polarized horizontally or vertically. And a quantum photon is a photon that is in a superposition between horizontal and vertical polarization. So we need devices that are able to emit photons that are entangled with other qubits, so that we can send those photons over the air or fiber optics. For example, here we can use NV centers. This is nitrogen vacancy centers in diamonds, where you excite the electron center with a laser beam, and when excited, it will emit a photon that is entangled with the with the electron spin inside. There are other techniques like trapped ions, quantum dots, which we will not go into those details. And once we emit the photon, as we said, we will send it over a quantum channel towards the destination. And that quantum channel could be a fiber optic or free space optical channel. So either in the free space or over fiber optics, we will be sending the single photons of light that carry the quantum state or our information. Then the receiver side needs a single photon detector in order to catch that photon when it arrives it needs to detect it and to be able to guide it through and perform operations on it and eventually perform measurement to be able to read the information embedded in the qubit. This includes optics and photodiodes, for example, among many other technologies. And one thing here is that quantum signals or qubits or photons, when they travel over fiber optics or in free space, they suffer from many losses in their transmission. And as long as they interact with their surrounding environment, they suffer from some loss called decoherence because of their interaction with the environment. So the longer the distance the photons travel, the lower their quality or fidelity. We call fidelity like quality of the entangled photon. So the lower their quality is, as their distance they travel is longer. That's why at some point, if your communication parties, the transmitter and the receiver, are very far away, your photon can't make it. It will be completely lost in the way if the distance is very large. That's why you would need to have some quantum repeaters in between, which are devices that perform entanglement swapping and BSM or bill state measurement, where it kind of does a swapping between two entangled pairs. So a repeater will get two entangled photons and do a swap of their states together so that it connects the photons on the far ends. And this is not very similar to the classical repeaters in wireless networks for two main reasons, which are the no cloning theorem and the no broadcast theorem in quantum information in general. The no cloning theorem says that an arbitrary qubit cannot be copied. So you can't say, I will get the photon, I will when it travels enough distance such that it suffered from losses and it can't continue. You can't just copy that the content of that photon into another photon and send the new one. You can't copy a quantum state. You will lose the information. Also, no broadcast theorem. You can't take a single qubit and try to make multiple copies and send each to a different user in the same time. That's why you need more complicated probabilistic operations like quantum bill state measurement and the quantum entanglement swapping, which are also not the main topic of this talk. So now, after we talked about the different components of quantum communication networks, what do we need to have a quantum network? We go to the future vision of the quantum network. So quantum communication networks are envisioned to build the quantum internet. The quantum internet is actually a large-scale network of quantum devices connected with quantum channels, and there's going to be for sure quantum repeater nodes in between. And having such a large-scale network, which will also include satellites that perform quantum communication from the space to terrestrial quantum stations, this will enable us to have quantum atomic clocks and quantum sensing, which is actually can be a replacement for GPS. And in addition to perform secure communications, as we said, sharing or distributing quantum computations over multiple devices at the same time, and in addition to many other applications that will emerge over time. So this is the vision for the quantum communication. And quantum communication networks today, they in general have four main advantages, as we just said. Like, they enable us to have higher throughput, because if you can send classical bit of 0 or 1, and your quantum state can actually carry 0 and 1 at the same time, you are able to actually, this is made very simple here, but you can actually have a much higher throughput or communication rate if you do it correctly. And unbreakable security is also based on quantum key distribution and the other techniques that enable you to communicate securely. And also, being able to distribute quantum computations, we can have more computing intensive networks that require less communication and more computing. And as we said, quantum computers happen to achieve very much faster computations than classical computers. But there is a fundamental research problem in quantum communication network research that we noticed in our recent article, which is quantum communication networks is a topic that's being addressed by two research communities. First of them is the classical communications community, people who work on 5G and wireless networks, routers, switches, and the quantum physics community, which actually works with the NV centers, trapped ions, single photons. They work with the hardware and the physics side. So we noticed that in general, the classical communications community, when they conduct research on quantum networking, there are too many works that assume many simplified assumptions that are not consistent with the physics nature of quantum networks. So the classical community, they have the expertise in doing like routing, resource allocation, scheduling of resources, but they are doing it in many works, not every work, but in many works, this problem is being done while ignoring or making very simplified assumptions on the available physics hardware or the nature of the physics hardware. And the quantum physics community, they care a lot about the physics details, the hardware technology, the limitations of the physics, and in some sense, they lack some of the expertise of the community in terms of routing and networking and scheduling, optimization of resources, resource allocation. So there is a need to actually bridge the gap between the two communities. We need to make sure that the quantum physics principles that stem from the physics nature of quantum devices, we need to make sure that they are respected when networking works are done. So we need to consider many physics principles like decoherence, as we said, which is lost due to the interaction with the environment, the probabilistic nature of the quantum operations, the no-cloning theorem, and the nuclear coupling, which is part of the NV centers in diamonds. So nuclear coupling with electron spins. So too many physics principles that one should consider. And if we do so, we will be able to develop physics-informed future quantum communication networks. We'll be able to have the quantum internet, hybrid classical quantum networks, and 6G communication that is secured by quantum key distribution, or QKD. So we are working in this article, our magazine article, on bridging this gap. So we identified multiple of the challenges that are in the literature kind of ignored. So the entanglement generation process itself, okay? This process, in terms of its nature, it requires multiple trials before it succeeds. This is probabilistic in general. So you do not directly generate an entangled photon whenever you try it. This operation is probabilistic and it does not always succeed. And the photon that you generate might not always be in the wavelength or frequency of your fiber optics or of your telecommunication band. So you will need to perform wavelength conversion operations, which reduces your probability of successfully generating a single photon. So one needs to consider those impacts when considering the entanglement generation, rather than just considering it as a successful operation that is lossless. And the qubits themselves, or the quantum states themselves, they have a very fragile nature. Whenever they interact with any surrounding environment, they directly lose their quality, and they can be easily lost. And they also have a very short lifetime, so they cannot maintain their coherence or their state for a long time without being affected, especially with the effects of the surrounding environment. So this is also something that some works actually ignore, and they assume we have qubits that have infinite lifetime, which is not true in the physics nature. Also, for the quantum memory, quantum memories that will store quantum repeaters. Actually, quantum memories is a fundamental part of quantum networks, which is where you store your quantum states. So those quantum memories actually suffer from decoherence and losses that must be encountered. You cannot assume that a qubit is stored infinitely for infinite amount of time without suffering any losses. Also, in your network losses, you need to account for the no-cloning theorem. So you take the probabilistic nature, the losses in the networks, the transmission operations, everything is lossy and many things are probabilistic that must be accounted for. And finally, for quantum repeaters, the entanglement swapping operation is also probabilistic in general, and it will affect the quality of your quantum states. So you need to make sure you account for that in your analysis. And we need to account for all the different losses that a quantum state suffers over this as it travels over distance. So those are some of the different physics principles and practical limitations in the physics hardware of quantum communication networks that need to be considered in order to perform physics-informed quantum communication works and research. So in order to be able to optimize the performance of quantum communication networks, to develop like efficient quantum communication networks, we need to identify like performance metrics that we can use as sort of objective function in our optimization problems. So in this paper, we actually introduced or identified multiple of the parameters or the performance metrics that one can consider, which actually stem from the physics nature of the quantum networks. So we have the delay, where the delay is takes into consideration the different factors that you have in terms of weighting and the storage in the memories, the lifetime of the qubits. The POS here is probability of success. So probability of success of the different operations that you have is also a performance metric. And the throughput, the rate that you are actually able to achieve, and the fidelity, which is actually the quality of the quantum states, corresponds to how good is your current quantum state from compared to what it should be. And when we have those performance metrics, we identify some control variables that we can actually control and optimize in order to optimize the performance of quantum communication networks. So some of the physics-informed quantum controls are first, if we consider there's like quantum error correction. This is a whole new field, not new, but a whole field that performs, tries to account for solving the errors and minimizing the effect of noise and losses, mainly noise that quantum states suffer from when they are transmitted over quantum network. So when you perform quantum error correction, the number of photons you use in the error correction technique, so you could be actually taking 3 qubits and you kind of purify them, and you get only one qubit out of the 3, but that one will have a higher quality. So how many photons do you need in this purification process? For example, you need 3, 4, 5. That question is also a control variable. The SPS, single photon sources for multiplexing. So you can consider a single photon source to be sending quantum states to a destination, and you can actually consider 2 single photon sources sending to the same destination. So if you have too many resources in your central node in the quantum network, you can allocate those resources to the different users, and that is also a control variable. The usage of your quantum memory, what qubits, what nuclear spins, or what memory slots that you will use in the available quantum memory to store your quantum states, and the storage time. How long do you want to store your qubit in the memory? That is also a control variable. And the coupling between the emitter and the electron spin, for example, in NV center, and the nuclear spins, for example, that is the memory. So there is degrees of coupling. We can change that with some techniques in the hardware. So this is also something we can control, which affects how good our memories are and how good the performance is. And in the same time, they will have some compromises. So having, for example, in the first one, having more photons in error correction, if we sacrifice more photons to get higher quality, we are getting higher quality, but we are sacrificing a little bit the throughput or the rate. So here it becomes up to the designer of the network to decide on what values to assign for those controls. And now I'm gonna shift gears to a work we did on entanglement rate optimization in heterogeneous quantum communication networks. I will briefly talk about this, where if we want to reap the benefits of quantum networks, we need to optimize many of the operations there. So some options are to optimize the entanglement generation process, to schedule quantum memory resources, to develop dynamic routing protocols that depend and vary dynamically with the current situation in your network. And here we focus on optimizing the entanglement generation process, where we are going to be varying the rates of entanglement generation and optimally utilizing the quantum memory and considering heterogeneous user requirements. That is, different requirements for each user, where each user would require a different number of entangled qubits, for example, with certain rates. And here we consider a system model that includes a centralized quantum node, which has an entanglement generation platform, a teleportation or transmission platform, and a large quantum memory, and that serves multiple users through quantum channels, and each user is at a different distance from the centralized node. This is a small-scale network, and each user will have actually a minimum required entanglement generation rate, and it will have a different channel attenuation coefficient. So when we generate an entangled pair of qubits, one of the Bell pairs, for example, so we have two entangled pairs. We will keep one of the photons, a single photon of the pair, will be sent over the quantum channel to the user, the desired user, and the other qubit, the other photon or qubit, will be stored in the quantum memory, and that photon that is transmitted over the quantum channel to the user will have this probability of successfully being transmitted to the user, and the one that is stored in the quantum memory will suffer from decoherence and will have this probability of actually being able to store it in the memory for duration tau, where R here represents the rate of entangled photons generated for user. Rj is for user j. So we formulated an optimization problem where we wanted to actually maximize the sum over all users for weighted sum over all users for these. This is the rate times the time, which means the number or amount of entangled qubits generated, and multiplying by the probabilities of success to see like what is the amount of successfully generated entangled photons. Subject to the first constraint here considers the quantum memory capacity. This could be like less than or equal, but we can assume like we want to always be maximally utilizing the available quantum memory. So C is the capacity of the memory, and we want the number of stored qubits to be satisfying this capacity, not higher than that. And the entanglement generation rate that we will we will find for each user must be above the minimum threshold for that user and below the maximum value, the maximum rate that the hardware can generate. So this optimization formula is actually a mixed integer nonlinear programming optimization problem, which is generally non-convex. So this problem corresponds to a convex nonlinear programming problem. If we do continuous relaxation, it becomes convex. So this is true for our problem in the range where tau, the duration of storage, is greater than 2 over R decoherence, the rate of decoherence in the memory. So we consider the branch and bound method to relax the integer restriction. And for that technique, if all the resulting values in your solution are integer, then the solution you got is optimal. And we use a software, optimization software with a integer point optimization method to actually obtain the optimal solutions. And here is a quick view of the results we got. So here we studied the impact of the lower bound of entanglement rate. So when we fixed the minimum required threshold entanglement generation rate for user 1, for example, in the red curve, we see that as the minimum required entanglement entanglement rate for user 2 As that increases, user 2 will be served with more qubits compared to user 1. You see the black curve where here is higher than the rate for user 1. And the impact of time duration, if we store the entangled qubits in memory for a larger time, and then we can't have very high entanglement generation rates, because we do not want to discard qubits. We don't want to generate qubits that we will discard and not use. So if we have our memory full, we will reduce the entanglement generation rate to make up for that. And the number of users, we notice that as we have higher number of users, we notice that at certain number of users, that as we have a shorter storage time for users in the quantum memories for the users, we notice that we get a higher objective function, which is the overall sum over all users entanglement generation, number of entanglement generation qubits. So a smaller tau or storage time, as we just said, will correspond to actually having a higher generation rate. And finally, we consider the impact of the distance of the users, where we notice that a photon losses for user J depends on Wj. The weight Wj here accounts for the importance of the user, and the losses are e to the minus beta g dj, where beta is the attenuation coefficient for user J and dj is the distance of that user. So we notice here that as the user has higher losses, it will be assigned lower rate, but that might not be a good requirement for the user to satisfy the user requirements. So that's where the importance of the weighting vector comes to make up for that. We don't want our optimization problem to always decide to give higher rates to users that have shorter distance and better channel conditions. We want to give the entanglement generation rates to each user based on the importance of the application the user is performing, in addition to the losses it suffers from. And finally, we notice that as we increase the entanglement, the quantum memory capacity that we have, we will be able to achieve better rates in entanglement generation for the different users in the network. So in conclusion, we optimize the entanglement generation rates, and this is an important process for the future of quantum networks, when we have devices that can control the entanglement generation rates. And the number of users a quantum node can serve heavily relies on the available quantum memory capacity. So if you have a very limited capacity, this will limit the number of users you can serve. And this is a motivation for many research that is ongoing on developing quantum memories that can store much higher amounts of quantum states inside. And we need to consider more complex network structures in the future, such as by incorporating more quantum repeaters in between the centralized node and the different users. And there is a need for further analysis of the delay associated with such problems. And now I will talk very briefly about future research directions. So after developing the physics-informed control variables and the physics-informed metrics of performance to evaluate the performance of quantum networks, we need to consider those in the analysis of quantum signals and information, which I will talk about later. Scheduling and resource allocation techniques is a really important aspect of research, in addition to routing, for example, that needs to be considered in quantum networks, and this needs to rely on the physics nature of the quantum hardware that we have. Finally, distributed quantum computing approaches and learning will actually need to rely on physics-informed metrics and controls so that they result in practical architectures. Regarding the first part with quantum signals and information, we published a preprint on quantum semantic communications, where we try to explore the embedded information in quantum signals and try to develop a semantic language. This is an ongoing project. And for scheduling and resource allocation, we are actually collaborating with Kenneth and Professor Towsley from University of Massachusetts Amherst and Tony Joe from MIT on doing resource allocation in heterogeneous quantum networks that is physics informed. That actually takes into consideration the physics nature and the controls the physics informed controls that we mentioned while doing the resource allocation. And this work is currently under preparation, should be ready in 1 or 2 months probably. And finally, for the distributed quantum computing, we actually developed work on quantum federated learning with quantum data, which is the first work in literature that generates a federated quantum data set, and apply that to a quantum federated setup. You can find the paper in this QR code. This work is actually something we are really interested in continuing in the future, and probably we are looking for collaborations, maybe with quantum formalism in the future. But this is the end of my talk. I thank you all for attending, and if you have any question, feel free to ask. Thank you, everyone.
Yeah, thank you. Thank you so much. It's very, very insightful. Let's see. I'm trying to get myself off the thing. Do we have any questions? Especially those guys coming from classical networking, because the purpose of this talk, as you mentioned, was a lot of people coming from classical networking making certain assumptions that do not, take into account the quantum physics side of things. So they end up having like a nice looking architectures and this thing, but if they cannot be implemented because of the limitations on physics, that's no good. Yeah. So
exactly.
yeah.
Thank you. That
any
was a
questions?
very
Yeah, go
clear
ahead, George.
exposition. Sorry. Thank you. That was a very clear exposition. As of now, I see nothing in the chat or in the Q&A, but people are welcome to submit questions.
And I must say the stage is also open if somebody wants to come in. Let's see if that's the case, and add a point to the thing, to this topic.
Yeah.
Let's see the settings. I believe the stage is open, so anybody who wants to join, make a comment or something, or add a point, can also do so. Let's see the chat. Any question? Well, I have a question while we are waiting. So,
Yeah, go on.
my question to you, Mehdi, people are talking. Yeah, go ahead. Is someone joining? Yeah, there's been a lot of positive announcements out there about like the current NISC devices, and also the potential that they have to provide some sort of computational advantage. So far we haven't seen anything concrete, but do you think distributed quantum computation using like NISC with the NISC hardware could actually be a possible route of actually getting some chance of getting some computational advantage before we have a fault tolerant machine?
Well, I mean, in general, like NISC devices, they are, yeah, there is no concrete, like very strong result that says, okay, they are all lossy, and they have, they require still the error correction thing. But having those devices with limited numbers of qubits, we can't perform like large scale problems yet. So the idea of distributed here would be actually very interesting to consider. Why do I need to wait until I have a very big quantum computer with millions of qubits that is able to run those computations? Why not actually distribute this computation in a way which requires a lot of work in the design of the computing algorithm itself to be distributed? But this is something we can do. So why not distribute the task over multiple NISC devices? Although they are lossy devices, they have limited number of qubits, but that would be like a good thing to explore, because we need to start early with this, since we know that the way like quantum computing will be in the future, you will not be like go buying your own quantum computer. It's gonna be all about using cloud service, quantum cloud services, and the cloud services, they will have multiple quantum devices together. So works in distributed quantum computing and distributed quantum learning will be fundamental actually for the operation of those quantum cloud centers. Currently, you can access a quantum computer, but like to distribute a task on multiple quantum computers, that requires a lot of research to be done. But that is a very promising approach for the future, especially with the limited number of qubits in the NISQ devices. That said, NISQ devices, I mean, it's clear for every researcher here that focusing on quantum error correction is a really fundamental approach. I currently started working on that in my research visit to Massachusetts Amherst, but that field is big, and there is a big room for contributions because we do not have like we're still in the early stage. We do not have complete error correction techniques and our quantum computers that can efficiently perform quantum error correction. So quantum error correction is a fundamental approach to develop those NISQ devices, and distributed quantum computing is a really important approach to actually connect the NISQ devices that we currently have and the future fault-tolerant quantum devices that we will have. And this can be done over both classical communication between the quantum devices, as we did in our quantum federated learning work, or through quantum communication networks, which is something we plan to study in the future. But the research directions are too many, and people are like just welcome to join.
Yeah, no, I completely subscribe to what you just said, and I guess another difficulty that we have right now to make it is different NISQ hardware architectures with different companies, just focusing on their own. They're not, I guess there have to be some other organization. Maybe this is where we have to think about standardization or like the thing in order to,
Yeah,
to work with these
yeah,
different vendors, to be able to network them.
yeah, that is actually a really important point. Yeah, I'm glad you mentioned that. So we mentioned that quantum computing, the technology, the qubits, they can be photons, but they also can be trapped ions. They can be superconducting qubits. They can be of too many different natures and can be implemented using different technologies. So each company actually adopts a model and is building and developing its own quantum computer using that technology. And here the debate, I mean, one can say that, okay, maybe we all agree on a certain type of quantum computers and we all collaboratively try to build it. But the main concern here is we do not know which one is gonna be the one to build fault-tolerant quantum computers. So that is the $1 million question. You can't know right now, at least. So each company is continuing its own quantum computer, and they are achieving great advancements. IBM and Google, Honeywell, there are many companies that are developing their own quantum computers. There is adiabatic quantum computing also with D-Wave company. So that company is adopting the adiabatic technique, and it is not shown that this technique is good for solving quantum optimization problems. So maybe each type of quantum computing platform will have some like advantage at a certain application. And like with the communication aspect, you have too many concerns about having kind of to being able to transfer a qubit from one type to the other. So communications is usually done over optical qubits with laser beams or single photons. But if I want to send a quantum state over a single photon, and then it will be received there on the user side, and the quantum computer there is a trapped ion quantum computer. So I need an interface here to take the information from the photon to the ion trap. And this is most of this part of work is on the hardware itself, the development of the hardware. But also in that, we are not sure like which types are easier to actually transfer between. So there is no like yes or no question here on with which one should we use or why should we use it. So people are like, each company is exploring its own, and having a standard technology in the foreseen future doesn't seem that's like something that is gonna happen. But I hope it happens sometime. Hi, Bernd.
Yeah, good
I
evening.
You have a
didn't.
question?
Hello, everyone.
Yeah.
Yeah, just have a few silly questions.
Oh, sure.
First one is what kind of quantum memory exists already? Because I think that seems to be a big problem, having sort of memory that has sort of any sort of reasonable half-life.
Yes. Okay. There are many types of quantum memories, but I will mention two. So one of them is we can use actually a fiber optical link. Okay, a fiber optical link. You can store a qubit or a photon inside it, such that it can just keep circulating inside. But that will make a lot of losses because of the interaction with the walls inside. That is one source of memory. There is this here, the diamond, the NV center. Okay, an NV center, there is like a vacancy and a nitrogen atom inside, vacancy in the diamond, in the carbon, and there happens an electron spin that is coupled to multiple nuclear spins that are distributed in the diamond. So the electron spin is the one excited with the laser such that it emits a photon, and that photon becomes entangled with the electron spin. But then you can actually swap or transfer that state inside the electron spin into one of the nuclear spins such that it stores it for long duration. So nuclear spins inside NV centers or diamonds are actually one of the very promising quantum memories, and there is a lot of hardware work here on how to perform decoupling between the different nuclear spins together, and decoupling between some nuclear spins and the electron spin, trying to actually increase the lifetime of the nuclear spin. And actually you can perform operations on a quantum state inside a nuclear spin, so it is a good memory that you can use. You can apply whatever you want in that memory. So those are two main types of quantum memories that I have now in mind. But the lifetime, if one reaches like a second or few seconds, that is gonna be a very big achievement if we get a memory with that lifetime, because we're talking here about like if you keep the qubit in the electron spin, the lifetime is going to be in terms of milliseconds. Then you go to the nuclear spin, and if you do proper decoupling and techniques, you could reach a little bit higher. I heard once that there is a work that managed to get like 10-second storage. I'm not 100% sure right now, but it's still early on until we get like lossless memories that have infinite lifetime. This is very far away. What was your other question?
Yeah, I've got a few. I mean, hopefully no one minds. The other one is the sort of the distance you can with current technology. What sort of distance can you cover to reliably transmit a signal? Is it just a few meters, or is it half a
Oh no.
kilometer, or roughly? So
Okay. The answer to this is gonna be a little bit depending on the technology you are using, but I will give you like two examples. There are many techniques with the NV centers, for example. Those are actually like lab scale experiments, but some of them like will developed a little bit to some kilometers. There are some implementations over Europe and multiple countries of country-wise quantum network. In the US now, there is actually, as I recall, they are working to establish a connection between the MIT campus and the Harvard campus, for example, a quantum link. And impressively, China, they have developed like thousands, like 1,200 kilometers communication, but that is kind of based on laser sources where you can get photons from the lasers, and they use free space. They did that they developed their Mikios quantum satellite, and they were doing a quantum key distribution from the satellite to terrestrial quantum station. and they achieved quantum communication over very large distances. But that is not the case with all technologies and the conditions that you have. So currently, like quantum key distribution, it is available actually commercially. One can buy device to perform quantum key distribution, and with some techniques where you can connect it to some optical fibers. So it is doable, but like to have a large scale quantum network with multiple nodes connected, like as in the quantum internet, this is a little bit far away, especially keeping in mind the idea of quantum memories, because we don't want to just send the qubits if we are unable to store them, or we will be like waiting until we get a request, then we send. So there is a lot of networking questions here that need to be answered. And that was actually one of the main motivations for this work, that there is a lot of need for the networking expertise in this field, but it needs to be done correctly. It needs to account for the physics nature, the specific quantum-based losses, and noise sources, for example. So that is the idea here.
Yeah, I mean, I get the idea. I mean, in the simplest case, like the Chinese, if you've just point-to-point communication, isn't it? But it isn't really a network. It's just point A, point B.
Yes.
Well,
Yes.
what we are interested in is like using existing networks. I mean, can you actually use existing fiber optic networks, or would you have to actually change the whole?
Okay. Yeah, you do not need to have. You do not need to actually change the whole infrastructure, but this is also a hardware issue where you can send a photon that has a quantum state, an entangled photon. You can send it over the telecom fiber optics. That works, okay? But for example, if we consider one of the most successful quantum single photon sources, the NV centers, the photons they emit, they are like with very low probability, around like 10% maybe or something like that. It's with this very low probability they will be emitted in the telecom wavelength. So you will need to actually either emit in different wavelength and do frequency conversion, which is also lossy, and your qubit is already lossy and fragile, or you will be waiting for a longer duration and making too many attempts until you successfully emit a photon at the telecom band. So photons can travel, like quantum entangled photons can travel over fiber optics, but it's gonna be like a challenge for the single photon source, for example, to be able to emit such photons. Other technologies like lasers can actually do that. You can generate photons that operate at the telecom band, and you can send them over fiber optics. That works. There are some implementations that consider kind of the coexistence between an electromagnetic wave and a quantum signal at the same time. So there is plenty of opportunities here, but the general answer is no. You do not need a whole new infrastructure, especially that you can use the free space optical quantum communication, which is free space, like as in wireless communications. And so the fiber optics you might need. I mean, there are some works, people who are specialized in optics and fiber optics. People are developing special fiber optics that are more suitable for certain types of quantum devices. But I believe like here in the future of quantum internet, I don't think like something will be dominating everything else. Like the quantum internet is not gonna be a replacement of the classical internet. In the same sense, like you will not always need quantum specific fibers. You can use the telecom fiber for some applications. So it will depend. So for some applications like quantum key distribution, you do not need very high quality or fidelity of your quantum states. If your quantum states happen to have like 85% quality, that is acceptable. Some other applications, especially in quantum computing, they would require you to have fidelity or quality of 99% or 98%. So depending on how much losses can you encounter, you might decide that, okay, I'm going to use the optical fiber, the regular one. or I might use the different architecture. So there is no one single answer here, but it's mainly related to the technology you're gonna use and the application that you want to deploy, but not in general. Like you can run quantum signals, send quantum signals over current optics. You can in general do that.
So do you think
I
it will
have
be a
just a
mix of sorry, somebody,
no,
sorry.
no, go ahead, go ahead, go
Yeah.
ahead. I will ask after.
So do you think it will be a mix of existing infrastructure and wireless technology, not, or do you think the old infrastructure will become outdated and actually it will all move to wireless technology somehow?
Well, we're seeing now like big telecom companies, they are investing a lot on the optics, the fiber optics infrastructure, because it has like its certain advantages, especially with the speed and communication and speed and rate. So like fiber optics is gonna be there, and at the same time with quantum infrastructure, quantum wireless signals like in free space quantum communication is still like for single photons, for example, is not that much explored. There is some analysis of the losses that the quantum signals will encounter in the wireless medium, like turbulence and pointing errors, stuff like that. But there is a need for more works in that area actually. But people are more saying that like we need to actually do it with the easy one, which is the fiber optics first, before we go into like wanting to practically deploy free space quantum communication. We are still like behind with developing it with the existing fiber optics. So let's build a larger scale networks first, and we can consider that free space optics. I mean, that one works well with satellites because of the free space. For satellites, the quantum signal will suffer less losses in free space and can travel longer distance. So there is a need for that approach too. But no, none is gonna like destroy the other approach. And the classical communications is still gonna be needed because it is expensive to send your data over quantum networks. It needs to be worth it. So if you need like you have applications that really require high security, for example, you want to perform quantum communication for security, then yeah, you will be very interested in sending your data over quantum communications. But some certain applications just don't care. So why going into the hassle of embedding the data into quantum signals and then sending them and taking the losses and performing error correction and the purification? Why that? Because this, like, we are still trying to deploy those things, okay? Until we reach a point where we can have low latency quantum communication, this is really far behind. Not now. So we just want to perform this. But regarding delay, this is too many operations where classical communications could be faster. So unless your application requires, you will be relying on the classical communications. That's why classical communications will always be there.
Yeah, thank you very
Yeah.
much. That's very helpful.
Thank you for your contribution, Berend. George, you wanted to ask something on the chat. Please feel free
Yes,
to jump in.
thank you. I have a more theoretical question, which is, does the physics of quantum mechanics potentially allow better distributed algorithms than the classical divide and conquer techniques like MapReduce?
Okay. Uh, in principle, the physics that like quantum physics principles like quantum superposition, for example, uh, gives a lot of promise in terms of parallelism. So this is the motivation for more faster computation, and one would expect that this will have like a superior advantage in distributed computing. But to be honest, I'm not the expert yet in quantum distributed quantum computing or distributed quantum communication in general. So I'm not 100% sure about like if the theory can actually develop novel algorithms that are superior to the classical divide and conquer or whatever distributed algorithms. There might be some works that actually investigated this topic. I haven't seen such works yet, but this is actually a very interesting idea to consider. Yeah, that is a nice way of thinking about it. Yeah.
Thank you. Because even in classical computing, we're not really taking advantage of fully parallel algorithms. We are either dividing them into pieces and doing them one after the other, or farming them out to multiple distributed locations and collecting them back. And both of those processes are inefficient.
Yeah, I see your point. Yeah, this looks like a very promising research direction that we're here, I guess. Yeah, like the distributed quantum computing approach is gonna be like an important direction, especially because of what I mentioned about quantum data centers or the quantum cloud that
Yes.
needs to sort of distribute computations over multiple devices. There is a lot of research on this field. I haven't explored it yet in depth. I started with distributed quantum learning with quantum federated learning, and I'm planning to further investigate this in the near future.
One thing also food for thought is how does the cap theorem, the classical cap theorem, fit into all this? Will it be like obsolete? This just food for thought.
The CAT theorem?
Yeah, cap theorem. Yeah, the the theorem. It's also known as I believe it's known as Brewer's theorem, which puts limitation on how much of the three things like consistency, availability, and the partition of tolerance. You can only have two things, not the three things.
Yeah, I see.
It's something.
Yeah, I think thinking about that will that could actually have like nice applications here with quantum
Just food for thought.
communication. Yeah, I like that idea. Yeah.
Yeah, that's the problem with giant distributed or sharded databases, that they can't communicate with each other fast enough to maintain consistency.
Yeah.
It's a very interesting no-go theorem. You can only have 2 out of 3.
Yeah. A challenge here would be like, as I just mentioned previously about the delay in quantum communications, the many operations we need to make sure we actually distribute high quality quantum states, that work, all those operations require some amount of time. So in distributed computing applications that require fast like synchronization and communication, so that will be a challenge there. That will be a big issue that one needs to design like distributed algorithms that would take this into consideration, for example, maybe. And I think the impact of delay will appear most significantly in computing or distributed quantum computing applications, because it is significant there.
Yes, I mean, even in the current world, between CPUs, memory, and distributed data, even if you have the very fast GPUs, graphic processing, to do the vector calculations, the bottleneck isn't there. It's in getting the data in and out of the GPUs. So this is going to be, as you explain, I can see that will all still be a problem in the quantum realm.
Yeah, I mean, you can think about the quantum computing here as QPU. They're considering it as QPU, quantum processing unit. So if we don't solve the issue of distributing a communication between the devices, we're still going to be having a very fast device that can't communicate with another device.
I guess this actually. Go ahead.
Go on.
It reminds me of the slogan from associated with some microsystem. The network is the computer. So I assume this also like it's also the only thing in the quantum realm.
Yeah, and actually here, I mean, if we notice in the classical community in 5G research and for 6G, semantic communication is a new technique that is being studied right now, because we are imagining future communication networks to have less communication and more computing. We want the end devices and the edge devices to be able to make more computations, faster, stronger computations, such that we minimize the amount of required communication.
Yeah.
So having quantum computers here will give us an advantage in terms of the computing, but the communication question becomes more challenging here. So if you will need less communication, but that is quantum communication. So if that is quantum communication, you have other things to worry about. So it's actually a compromise here.
Fascinating. Does anyone? I know I'm aware of the time, Mehdi. Your time we're
Yeah,
like
I see.
almost 20 minutes over.
Yeah.
Well, I mean, I would stay here, listening to all this, participate in all this interesting stuff about this very nascent and exciting topic of distributed quantum computation and
Yeah,
and so on.
indeed,
Does
yeah.
anyone have any other question before we close? George or Berend as well, or anyone else on the audience?
Somebody
Okay, maybe I
speaking?
will ask a final provocative question. No, Berend, go ahead then.
Yeah, the final question. I'm quite interested in quantum sensing. You mentioned earlier on the possibility of connecting sensors, because I'm always wondering, is it possible to get a signal from a sensor, a quantum sensor, keep it quantum, and
Yeah.
then maybe take it to a quantum computer? How realistic
Yeah.
is that this existing technology? What work is being done on this?
Actually, there are some quantum sensors that exist right now. That is one thing. And quantum sensors happen to be like extremely more sensitive to electromagnetic radiation, for example, as one example. So with a quantum sensor, you will be able to sense things in a much better way compared to classical sensors. But then comes the question of using that data. So quantum sensors might need to communicate together to be connected, for example, over a quantum network. Actually, like distributed quantum sensing is one of the applications of quantum communication networks. It's one thing that we consider. Actually, also in the last work here on quantum federated learning with quantum data, the quantum data that I generated here is actually resembling of quantum states coming from quantum sensors. So I'm saying here, okay, let's say I have sensors that got the data. So, and it is connected with a quantum computer, for example, and I want the multiple sensors or devices to learn together so that each sensor benefits from the available information with the other sensor, so that we did this federated learning to distributed learning between the devices. So yeah, there are some technologies actually also, again, back to NV centers or in diamonds, they can also be used as quantum sensors for electromagnetic radiation. There is a lot of work on this field. There is interest in this. It is very practical, and it's important for quantum atomic clocks and the quantum positioning system that is being investigated mainly by the army, because it is actually a good replacement for the GPS in case GPS is jammed, for example. So then quantum sensors could allow you to actually perform positioning and high quality sensing. So this is a whole big area. So you see, like in that talk, we have mentioned like many directions. Each of them is a whole world. Quantum error correction is a whole world on its own. Quantum key distribution or quantum cryptography, that's a whole world with companies and expert people in there. And distributed quantum computing is something. Building quantum computers is something. Doing on the theory of quantum algorithm is another thing. Quantum communication networking is something. Quantum machine learning is a field. Quantum sensing is another field. So I'm trying in my work to kind of uh, like bridge the gap between multiple of these with the reality that we have in wireless networks. So in quantum communication networks with quantum machine learning. So if we need to distribute quantum machine learning tasks, we need to communication between the different quantum devices. That's how I integrate quantum communications with quantum machine learning and computing. And at the same time, those devices will take the quantum data, and quantum data could be coming from quantum sensors, and that's how you can integrate quantum sensors with them. And quantum algorithms and quantum computing can be applied to current wireless communication classical problems. You can solve the optimization problem using a quantum computer or a quantum optimization algorithm. But that is also another area. You could be like just expert in quantum optimization and running quantum algorithms on quantum computers and try to solve classical problems on quantum computers. That is also another field. So everything is kind of connected and disconnected at the same time. But yeah.
Well, which creates a huge opportunity really for people to bridge the gap, because it also shows how early the industry is, and it's not done deal yet. So no one is ahead. It's like it's still like also opportunity for collaboration, because people cannot work
Yes.
just in silo. So yeah.
Yeah, actually,
George,
and
thank you.
here. First, thank George for copying the QR code of the paper. And here, one more thing is, like, for me personally, like, I have the background in classical communications and in security, so I found like the perfect fit, like the new research direction and new technology that needs a lot of expertise is quantum communications. I got a lot excited about this, and I focused on building like a background in quantum physics, because I said if we are gonna work in quantum networking, and I have a classical background, I mean, one needs the correct background in quantum physics, and quantum hardware, for example, so that we do it right, we do it the right way. So having like the background of classical communications actually helps me in thinking about some problems that people in the physics community wouldn't be much interested in. So when we collaborate together, we happen to have like different approaches for certain problems, which leads to great achievements.
Absolutely. So
Yeah.
go ahead, George. Any final comments? I know we have gone over the time, but it's been like a fascinating discussion. George, you want to ask anything or add anything before we close? I actually have a question, a final provocative question. You don't have to answer now, Mahdi.
Okay.
You talk about the $1 million question about which architecture to building a quantum computer will be a winner. So if you could bet on $1 million, based on what you see so far, which one would you say is a little bit ahead? Or thing? I know it's a very
that
hard
is
thing.
a very tough
Okay.
question. I have been actually in discussions with IBM people a few months ago, and I asked them this. Like I said, like every company has its own architecture. Which one should we consider for quantum communication? Which one should we rely on? Like, why not unite all the efforts? And like they said the same thing. Like it's difficult to have like a single one, and maybe it's better to try all of them. But the results of superconducting quantum computing are very promising. They look very futuristic, actually. Superconducting qubits. I mean, I'm not sure if I would bet on that, but that is very promising, you know.
Okay, that is fair enough.
Yeah.
Well, thank you so much for the insightful talk, and we
Thank
look
you for
forward to
hosting
having
me.
you back again. In the future in the near future, to update us in some of the work that you are doing, especially in respect to distributed computation.
Yeah, thank you
So
so
in
much. Thank you
federated
for
quantum
hosting
machine
me.
learning in particular. Yeah,
Thank you for hosting me and giving me this opportunity. And I look forward to further collaborations in the future and more talks. Thank you so
absolutely.
much. Thank you, everyone, for being
Thank you.
here.
Thank you, everyone. Thank you, Matter. And thank you, George, as well, and Baron and everyone on the audience. And we catch up on the next Q&A. Or Q&A. In the next webinar. Thank you. I see you all.
Thank you.
Bye.
Thank you, guys. Goodbye.
Yeah, cheers.